Well, welcome back, everyone. Here's that same data I gave you at the very beginning of this sequence of lectures, describing the occurrence of headaches among 100 students who are being followed over time, over a 7-day period, measuring the occurrence of a first headache. And as we noted before, 15 of these students of the 100 developed headaches, and then the last session we talked about measuring something called cumulative incidence, or estimated risk, by dividing 15 by 100 and reporting the proportion of people who developed headaches during the 7-day period of follow-up. We were using as a point of reference the total size of the population at risk, 100 people, of which 15 of them developed headaches sometime during the 7-day period. Well, here's another option you could do. We could use as our point of reference not the number of people, but the amount of follow-up time that was observed in this study. Remember, each person has a timeline. That timeline tells you how long that person was followed, either until they developed a headache or the study end. So another option for measuring the to quantify the incidence of headaches in this study is to measure something called an incidence rate. What we'll compare is that what we'll measure is 15 students developed headaches when I observed 645 person days of observation. Now, where did I get that 645 person days of observation? Let me go back to the original display of the data. Remember, each person is followed either until they develop an event or the study ends. Each person is giving me person time. Person number 1 gave me 1 person day of follow-up before that person unfortunately developed a headache. Person number 2, 3, and 4 also gave me 1 person day of follow-up. So those 4 people in total gave me 4 person days of follow-up. Person number 100 gave me 7 person days of follow-up. So what I could do is I could add up all the person days of follow-up, add up all the numbers in this last column. And if I added correctly, which hopefully I did, you'd end up with 645 total person days of observation. And what did you observe? Out of that 645 person days of observation, 15 new cases of headaches occurred. So we can define something called the incidence rate as a ratio, something divided by something else, where in the numerator we put the number of cases that developed, 15, but we're not putting that over a denominator of 100 people, we're putting it over a denominator of 645 person days. Well, if you go through the calculation and divide 15 by 645 person days, 15 divided by 645 would give you the value of 0.0233 for every 1 person day of follow-up. Well, I could multiply 0.0233 by 100 and say I observed 2.33 cases of headaches occurring for every 100 person days of observation. So incidence rates are commonly reported as number of cases per some period of follow-up, some period of person days, person months, person years, where they're usually expressed in multiples of 10. So many cases for 10 person days or 10 person years, so many cases for 100 as I have here. So what we observed were 2.33 new cases of headaches for every 100 person days that I followed, that I observed. Now, there is a limitation. There is a potential problem with this calculation. This number, 2.33 cases for every 100 person years, doesn't take into account that 4 of my people developed a headache on the first day, and only 1 person developed a headache on the 7th day. So maybe the risk of developing headaches on certain days during the follow-up were greater than on other days. Maybe your chances of developing a headache during the early part of the study, in the first day, might have been greater than in the other end of the study, because maybe you built up a tolerance to our lectures, and therefore your risk of developing a headache further on during time was less than it was early in the study. Well, that single number, 2.33 cases of headaches for every 100 person time, doesn't reflect the possibility that the incidence rate could be different at different periods of time during the follow-up. So what I want to introduce to you is the notion of an incidence rate function, a function of time. So we'll let IR parentheses T stand for the incidence rate function, the value for the incidence rate at a specific point in time T, where T could be the first day, or T could be the 5th day, or T could be the last day, the 7th day of follow-up. And maybe the values for those incidence rates might differ at different points in time. Now, the statisticians will call this incidence rate by a different term. They call it a hazard rate. And therefore, the incidence rate function is a hazard rate function. And if you ever go on and take a course in survival analysis, you'll see the hazard rate function plays an important role in building survival probability curves or regression models or things like that. But whenever you see the word hazard function in a statistical paper, just think of it as an incidence rate function. What it's supposed to describe conceptually is the risk, the occurrence of disease at a particular point in time during the follow-up. So our follow-up was 7 days long. What we could at least conceptualize is the risk of getting a headache on the first day, or the risk of getting a headache on the second day, or the risk of getting a headache on the 5th or 6th or 7th day. Those values for the incidence rates might not be the same on every day. There might be periods of time when you're at very high risk for developing headaches, and other periods of time when you're very low risk. And the incidence rate function ideally is going to reflect those different values for the incidence at different points in time. What we can think of the incidence rate in some sense as an instantaneous risk of developing a headache at that particular point in time. We can think of it, what's the risk of developing a headache on your first day? What's your risk of developing a headache on your 3rd day? What's your risk of developing a headache on the 7th day? That's what the incidence rate is trying to measure, the occurrence of disease at a particular point in time among people who were at risk for developing disease at that point in time. So realize when you break your follow-up periods into different subintervals of time, the population at risk at the beginning of each of these subintervals might be different. At the beginning of our study, we had 100 students. All of them can tell us something about the risk of developing a headache on the very first day. The 4 people who developed headaches on the first day are no longer at risk for developing a headache on the 2nd day. So the population at risk at the beginning of the 2nd day is no longer 100 people. It's down to 96 people. So as you follow people over time and try to measure incidence rates at different points in time, realize your population at risk is going to get smaller as you follow people longer and longer, because once you develop the disease, your first headache, you're no longer at risk for developing a first headache. So what might happen is that not only is your population at risk getting smaller, your value for your incidence rates might be changing over time. There might be critical periods where your risk is very high or when your risk is very low. So let me try to describe that notion of the incidence rate's value varying over time by giving you 3 examples. What I want you to do is to consider this graph and consider these 3 different pictures, or pictures of 3 different incidence rate functions. The first one I want you to think about is, let's imagine you look at people who are undergoing a major surgery, a bypass surgery, or they're having heart disease and they're being operated hopefully to solve their blockage in their arteries. There's going to be some bypass surgery, which is a non-trivial surgery. Or maybe they're undergoing a transplant. They're having a kidney replaced or something like that. But let's imagine in your minds people undergoing an operation that has some risk involved in it, and it's given to people who need this operation. It's the only chance they might have for improving their life and maybe extending the years of life. So imagine in your minds what the incidence rate function would look like for a person undergoing this major type of surgery. Because they're very sick, and that's the reason they're having the surgery, and because the surgery itself has some risk involved with it, early on during the study, there may be a period where the incidence rate's very high. But if you make it off the table, if you survive the surgery, and you survive the following days or weeks in the hospital when you're closely being monitored in the intensive care unit, and you're finally discharged, You're being discharged because your surgeons and the other physicians feel that you've survived this high-risk period. You're going to have the benefit of that surgery. Your incidence rate in the coming weeks, months, or years might suddenly be a very lower value, your incidence rate of dying. But as you age, your risk of dying increases. So if you measure the incidence rate well on into the future, 10 years after the surgery, 20 years after the surgery, those people are now 10 years older, 20 years older, their incidence rate of dying is going to be a higher value. So it could well be that your incidence rate function looks like a roller coaster. It could be high during some periods of time, low during others, high again during others. If that's the case, remember the quote I gave you in the last series of lectures when I talked about baseball. And I talked about a baseball manager saying that if you have half of your body stuck in a ice bucket and half of your body stuck in a fire, half of your body's freezing, half of your body's burning up, on average, you might say, I'm feeling fine, because the burning up part of your body is counterbalancing the freezing part of your body. But that average is not a good description of the fact that half of your body is suffering because it's frozen and half of it is suffering because it's burning. So when you calculate a single number, as in the previous example, 2.33 cases of headaches for every 100 person days of follow-up, that one number cannot reflect different values for the incidence rates at different points in time. It'll turn out that that one number is an average of the high incidence rates that exist around the time of surgery, the low incidence rates that exist in the months after surgery, and the higher incidence rates that exist well down in the future. And that's the problem with using one single number as an average when you're averaging different values together. So we epidemiologists like using averages, but we should use them conservatively when we think that that one number is describing what's going on, in this case, in different parts of the follow-up period. And we're talking about different values for the incidence rate function. Well, let me give you two other examples. Example 2 might just be, imagine your risk of dying during your life. Well, when we enter this world as newborn infants, unfortunately some of us don't survive. So there is a small but non-zero risk of dying during childbirth. But if you make it through childbirth and you make it through the next couple of days and you're discharged home with your mother and father, chances are you're a healthy baby. Chances are your risk of dying in the coming weeks, months, years are relatively small. But as you go through adolescent age, you suddenly go into a period of increasing risk. Traffic accidents might be the major cause of mortality among teenagers in our country. Drug overdose might be a major problem in some parts of our country among teenage people or early adult people. The point being is that as you age, your incidence rate starts to increase. And it's going to continue to increase. The chances of you dying, all things being equal, when you're 50 years old is probably less than when you're 60 years old, less than when you're 70 or 80 or 90 years old. Marcello talked about life tables. That gives you an idea of risks of dying at different periods of time. Maybe the incidence rate function begins to plateau off after a certain age. It still might be increasing, but not at the same rate. So this might be a typical incidence rate function to describe overall mortality during a person's lifetime if you followed a group of people from birth until death over, say, a 100-year period. The last one I want you to consider is maybe the hardest one to imagine. It's a picture where the incidence rate value doesn't change with time. During the very beginning of the study, the incidence rate is some value, and that same value exists for people who are still alive and at risk at the end of the study. It's a constant incidence rate. And for a study that has a very long follow-up, this type of picture is probably not going to hold. Because one of the problems with following people for very long periods of time is they get older. In the Framingham Heart Study, if you were planning to follow people for 20 years, or in your data set you can follow them for 24 years, at the end of the study people are 20 years older than they were at the beginning of the study. And your risk of dying is going to be higher at the end of the study than at the beginning of the study. So this might not be a reasonable incidence rate function to describe the occurrence of any outcome when you're following people for long, long periods of time. but for a short period of time. You're following people for a couple of months, a couple of years, maybe this is a reasonable assumption. This curve, which has a constant incidence rate, meaning the incidence rate's value doesn't change during the period of follow-up, is the only time you can argue that if I follow 10 people for 1 year, I observe 10 person years of follow-up. If you follow 2 people for 5 years each, you observe 10 person years of follow-up. And if someone else follows 1 person for 10 years, they observe 10 person years of follow-up. In which situations are those 10 person years of follow-up exchangeable? When doesn't it matter whether I'm following lots of people for a short period of time or few people for the long periods of time? It doesn't matter when you have a constant incidence rate. So in a constant incidence rate, you might as well combine all the person time that happened either in the beginning of the study, the middle of the study, or the end of the study into one total number of person time. Because all those person time that came from different parts of the study are reflecting the same value for the incidence rate. So when does it make sense to count all the cases that occur in a population that's being followed up over time and divide by all the person time, like we did in that first example when we took the 15 cases of headaches and divided by the 645 total person days of follow-up, when we believe we have a constant incidence rate function? Because then we're getting the one number, 2.33 cases of headaches for every 100 person days of follow-up, that holds true at any time during that follow-up period. So that one number makes a lot of sense when we have a constant incidence rate function. It makes less sense when we have an incidence rate function that looks like a roller coaster. In that case, we're essentially coming up with an average. So how are we going to calculate incidence rates numerically? Well, it depends on whether we believe the incidence rate function is constant or not. If we don't think it's constant, and think of that first example, the example of those people undergoing a severe surgery which has a certain high risk of mortality associated with it, the best way to describe the incidence rate in that first example might be to calculate an incidence rate at the very beginning of the study, for the first few days or the first few weeks of study. That's the high risk period. Again, another calculation in the middle part of the periods when people are at low risk, and maybe another one at the end when they're at high risk again. What we could do is, if I wanted to calculate the incidence rate at a particular point in time, what I'm going to do is I'm going to pick an interval around that time. If I want to know the incidence rate, say 3 months into the study, I'll look at people who were alive and at risk for developing this outcome at around 3 months during the follow-up period. I'm going to look at all the cases of disease that developed in that interval of time, around 3 months, maybe the week before up to the week after of their 3-month follow-up point in time. And I'm going to divide that by all the person time I see in that interval. So that calculation I did using all the person time for the headache data, I could do it in separate intervals if I believe the incidence rate function is changing over time. Now, how long should this interval of time be? Should it be a week long? Should it be a month long? Should it be a day long? Well, it depends on how quickly I think the incidence rate function is changing in time. If I'm coming up with one calculation and saying that's the incidence rate at time t, I want to use person time observed around time t, for which I think the incidence rate wasn't changing that much. So if it doesn't change that much in a week or 2 weeks or something, I can measure all the person time the week before time t and the week after time t. That's how I can measure the incidence rate at time t. So in calculations, what we're going to do is we're going to calculate the incidence rate at time t by using this formula. Look at an interval of time around time t, say around 3 months into the study. Find out how many people developed disease during that interval and divide by how much person time I observed during that interval. So notice I'm dividing by person time. I'm not dividing by people. If I'm interested in the incidence rate 3 months into my study, maybe I started out with 1,000 people. Maybe 3 months into the study, I only have 900 people still at risk for developing disease. 100 people already developed the disease. So I have 900 people at risk. Why am I not putting in the denominator 900 people? Why am I putting into the denominator the person time I observed from those 900 people? Well, the reason is the following. Let's suppose you had 100 people who were at risk of developing disease around a time t, say the 1 week period around t. They're the population at risk for developing disease at that point in time, that particular point in time t. And let's suppose 5 people develop the disease. What's the value for the incidence rate at that particular point in time? Well, according to the previous formula, it's going to be 5 cases of disease developing in that interval divided by how much person time I'm going to observe during that interval. I had 100 people who were at risk at the beginning of the interval. The interval was going to be a 1 week period of time. If I have 100 people, follow them for 1 week, I'd expect to see about 700 person days of follow-up. So my incidence rate would be approximately, and that's why I have these squiggle lines here to represent approximately 5 cases divided by 700 person days. Now, why do I say approximately? Because I really don't expect to see 700 cases of disease during that 700 person days of observation during that 1 week period. Because 5 people developed disease during that 1 week period. Those 5 people, if they developed it at the beginning of that week, do not give me 7 days of follow-up for which they are at risk of developing disease. So what I'm doing here is I'm taking 100 people, multiplying them by 1 week being 7 days. Therefore, 1 times 7 days is 700. But realize 5 of these people are not going to give me a full 7 days of follow-up. Their follow-up is going to be shorter than 7 days. How much shorter? Well, it depends when they develop the disease. They might develop the disease at the very beginning of the interval. They might develop the disease at the very end of the interval. But the point is, this is an approximation because I don't know exactly how many person days of observation I'd observe in this case. So my calculation approximately would be 5 cases for 700 person days of observation. But now let's suppose you come along and you want to measure the incidence rate at time t also. But you think the incidence rate is flat for around 2 weeks long. So your interval of time is going to be 2 weeks, not 1 week. What's your calculation for your incidence rate? Well, you start out with those same 100 people at the beginning of the 2 week period now. I told you that 5 cases developed it during the first week, the first 7 days. You're following people for now twice as long. You might approximate that you'd expect to see twice as many cases, 10 cases rather than 5. So you would calculate your incidence rate to be 10 cases divided by not 700 person years, 100 people being followed for 7 days, but now the people are being followed for 14 days. So you expect to see 1,400 person days of calculation for your denominator. Your incidence rate would then be 10 divided by 1,400 person days. But 10 divided by 1,400 person days is the same as 5 divided by 700 person days. So if I follow people for a longer period of time than you, and we both believe the incidence rate is constant, we would like us to get the same answer. And we will do so if we have in our denominator person days. If we just put into the denominator the number of people we started out with, 100, my cumulative incidence would be 5 out of 100, 5%. Your cumulative incidence would be 10 out of 100, 10%. Why are they different? Because I'm looking at a 1 week cumulative incidence, and you're looking at a 2 week cumulative incidence. We're mixing apples with oranges. We're measuring 2 different cumulative incidences, one for 1 week, the other for 2 weeks. But the incidence rate calculation should approximately give us the same result. So this is the way we could estimate the incidence rates if we believe the incidence rate function varied over time and we wanted to calculate separate incidence rates for separate periods of time. If we believe that the incidence rate is flat, that bottom curve we looked at, then we can combine all the cases into one number. It doesn't matter whether they occurred early in the follow-up or late in the follow-up. Divide by the total number of cases, the total number of follow-up time, whether it was early in the study or late in the study, and come up with one number. We can call that the incidence rate It's a single value that we assume is reflecting the incidence rate at any point in time during our follow-up period. So when we calculate this single number incidence rate, or when you see it in publications, basically what it's describing is what the value would be for the constant incidence rate if it existed over the full period of follow-up. If, on the other hand, the incidence rate function is not flat, say the first case or the second case, this single number, the incidence rate, is going to be an average of the different incidence rates that exist at different periods of time. So, for example, going back to those three instances or the three diagrams I give you, if you calculated a single incidence rate from data that was derived from following people after they underwent a serious type of surgery, you're going to come up with one number. That one number cannot reflect the high incidence rate of the early part of follow-up and the low incidence rate in the middle part of follow-up. What you're ending up with is a single number, an average of the high and low incidence rates that exist at different periods of time. Same thing if you calculate a single incidence rate by following people over time from birth until they died. That one number would overestimate the low incidence rates that exist during childhood with the higher, and underestimate the higher incidence rates that exist in the elderly. Only in this last case does it really make sense to summarize the incidence rate into one number. And to drive that home, I'd like to give you one last example to see if we can get the flavor of calculating incidence rates. Let's suppose we had three populations, three different data sets in front of us. One is called population A, one's called population B, one's population C. Each of them has 100 people in it at the beginning of a study. In population A, 10 people died during the first year, 10 during the second, 10 during the third, 10 during the fourth. So during the 4 years, 40 people die. In the second population, different 100 people. Only 2 people die in the first year. Only 2 people die in the second year. Only 2 in the third year. But then 34 people die during the fourth year. And finally, in the last population, population C, 10 people die in the first year, 9 in the second, 8 in the third, and 7 in the fourth. Well, let me ask you, if you could be a typical person from either, let's just look at populations A versus B right now. Let's forget for the time being population C. If you could be a typical person from that population, so that the mortality experience of the 100 people in population A describes your risk of getting disease. Or if you're in population B, those 100 people describe your risk of getting disease. Which population would you rather be in, A or B? Now, when I ask people that, they typically say, I'd rather be in population B. And I ask them why, because what's the 4-year cumulative incidence? What's your risk of developing this outcome during 4 years of follow-up? For population A, it's going to be 40 divided by 100. For population B, it's going to be 40 divided by 100. So no matter whether you're in population A or population B, your risk of getting this disease is 40% in the next 4 years. One's no better than the other if you're talking about cumulative incidence, if you're talking about estimated risk. But people who choose population B usually say so because they say, gee, look how we got to that 40% cumulative incidence. During the first year, only two of us developed the disease. During the second year, only 2 of us developed the disease. In the third year, only 2 of us developed the disease. So during the first 3 years of follow-up, population B looked a lot better than population A because fewer people were getting disease. But then when you go into your last year, if you survive the first 3 years and you're still at risk for developing disease in the 4th year, now which population would you rather be in? Would you still rather be in population B, or would you rather be in population A? When I ask students that question, they'll say, gee, now I want to be in population A, going into my 4th year. Because in population B, 34 people, lots of people are getting disease in that last year. That's the difference between incidence rate, which is describing the instantaneous risk of disease at different points in time. And for population B, it's very low in the first year, very low in the second year, very low in the third year, big in the 4th year. And cumulative incidence, because both A and B have the same 4-year cumulative incidence. So let's measure incidence rates in these populations. Here's population A. Remember, 100 people, 10 people die each year. Let's measure the incidence rate during the first year, during the second year, during the third year, during the fourth year. During the first year, we start out with 100 people, and 10 of them get disease. Let's suppose disease is death. So 90 people don't die. 90 people give me a full year of follow-up. 90 person years altogether among the survivors. These 10 people, we don't know when they died from these data. Let's suppose they all died halfway during that year. So each of them lasted a half a year before they died. I have 10 people, each giving me a half a year of life, of follow-up. That's 5 extra years in total. So I would observe 95 person years of follow-up among those 100 people in the first year. The incidence rate would be 10 cases of death divided by 95 person years. That's 0.11 deaths for every single person year if I divide 10 by 95. So 10 divided by 95 person years is the same thing as 0.11 deaths for every 1 person years. Now what's the incidence rate during the second year? Second year we have 90 people still alive and kicking. They're at risk for dying in the second year. 10 people are no longer at risk. They've died already. Of those 90 people, 10 died. How much person time would I expect to see in the second year? Well, if 10 died out of 90, that means 80 survived. 80 people gave me a full year of follow-up. The other 10 gave me, on average, a half year of follow-up. In total, another 5 years. So those 10 cases of death would occur from 85 person years of follow-up. And the incidence rate, therefore, would be 10 divided by 85 person years, which is equal to 0.12 deaths for every 1 person years. And I can do the same thing for year 3 and year 4. What I want to draw your attention to is notice the incidence rate value is increasing. During the first year, it's 0.11 deaths for every 1 person year. That jumps up to 0.12. That jumps up to 0.13. That jumps up to 0.15. Despite the fact that the same numbers of people are dying every year, constant number of deaths. Why is it that we're getting higher incidence rates later on during the study when just as many people are dying at the end of the study, in the middle of the study, as they did at the beginning of the study? And the reason is the population at risk is shrinking. Once you die, you're no longer at risk for dying again. So at the beginning of the first year, we had 100 people alive and kicking. At the beginning of the second year, we have only 90. Less person time being observed during the second year. Same number of deaths, same numerator, 10, happening out of fewer person years. Incidence rate's going to get higher. Now, if you come along and calculate a single value for the incidence rate, total number of deaths, 40, divided by total number of person time, by adding up all the person years, 320, you'll get a value, 0.13 deaths for every 1 person year, and that 0.13 is an average. It's an average of the 0.11, the 0.12, the 0.13, and the 0.15 incidence rates that exist at the 4 different years of follow-up. So that's how you can measure the incidence rate function for population A. We can do the same thing for population B. Different 100 people, 2 of them die during the first year, 99 don't, 98 don't, 98 people give me a full year, 98 person years. Those 2 people who died each give me a half a year, and totally give me another year. They give me a total person time of 99 years. Incidence rate would be 2 cases divided by 99 person years, or 0.02 cases for every single person years, a small number. I can do the same calculation as I did before for years 2, years 3, and the incidence rate stays small. Each year the incidence rate calculated to 2 decimal places to describe the incidence rate for a single person year follow-up is about 0.02. But notice what happens in the last year. Last year, 6 people have died already. We only have 94 people left at risk for developing death in the 4th year of follow-up. 34 of them died during that period. That's a high number of deaths during that year, higher than what happened in the previous 3 years. That means 60 people didn't die. They each give me a year of follow-up. The 34 people each give me a half a year. That's like another 17 years in total. I observed 77 person years in total. What's the incidence rate for population B in the 4th year? It's going to be 34 deaths out of 77 person years of follow-up. Notice it's 0.44, much, much higher than what was existing in the 1st, 2nd, and 3rd year of follow-up. That's why I don't want to be in population B if I survive my first 3 years. I wanted to be there for the first 3 years where the incidence rates were small, but not in the 4th year where the incidence rate's very, very high. But if I try to combine all the cases, 40, and all the person time, 368, into one number, the single average incidence rate, I come up with a number of 0.11 cases for every single person year of follow-up, and that 0.11 overestimates the incidence rates that were low during the first 3 years and dramatically underestimates the incidence rate in the 4th year. So again, think of that person. Half of them is burning up and half of them is freezing over. Averaging doesn't make much sense in this case. But that's what that single incidence rate calculation will give you. Well, finally, if you just look at population C, and I'm not going to go through the calculations, the incidence rates are almost constant. 0.11, 0.11, 0.11, 0.10 for the 4 years of follow-up. They're all about 0.10. If you take all the deaths, 34, divided by all the person time, 327 person days, you'll get roughly that same number again, 0.10 deaths for every 1 person years of follow-up. Here this one calculation, all cases divided by all person time, makes sense. But notice what's happening here. To get this constant incidence rate, or nearly constant incidence rate, the number of deaths was decreasing from 1 year to another. And the reason it had to decrease, in order to keep the incidence rate the same, since the population at risk was decreasing, the total number of person time was decreasing. To get the same incidence rate from 1 year to another, where in the 2nd year the total number of person time is smaller, the total number of deaths have to be smaller. And that's why population C probably is an example where the incidence rate function being flat is a reasonable assumption to make. And the calculation of a single number, 34 cases, divided by 327 person years of follow-up, 0.10 case for every single year, is a good description of what's happening at any time during that follow-up period. So, a couple of comments. As I said, for population C, incidence rate appears to be constant. In that case, let's add up all the cases, get a total number of cases, 34. Let's add up all the person time, whether they happen in the beginning of the study, the middle of the study, the end of the study, 327 person days. Let's take total cases divided by total amount of person time, 34 divided by 327 person days, and we get that number 0.10 case for every 1 person year, which if I want is the same thing as 10 cases for every 100 person years. That's what my estimate is of the common incidence rate. For a different population, like population B, if I do this calculation, what I'm getting is an average of the different incidence rates that were very low in the first 3 years and very high in the 4th year. Numerically, really what it is a weighted average. Because if I took all the cases, 40, that I observed in population B, and divide by all the person time I observed in population B, 368 person years, and represented that as one number, 0.11 cases for every 1 person years of follow-up, mathematically, that's the same thing as taking each of my 4 separate incidence rates that existed in the 1st year, the 2nd year, the 3rd year, and the 4th year, weight them by their person time. So I'll take the first incidence rate, which was 2 cases for 99 person days of observation, and multiply it by 99 person years, weight it by the total number of person years that went into that calculation. Do the same thing for the 2nd year. The incidence rate was 2 cases out of 97 person years of follow-up. Weight that by the 97 person years. Do that for the 3rd and 4th and add those together. That's a weighted summation. Each incidence rate is being weighted by a number, the number being the total amount of person time that went into that calculation. And then divide that entire quantity by the sum of the weights. That's what a weighted average is. And you'll get the same number, 40 divided by 368 person years. So whenever you use this calculation, total number of cases divided by total amount of person time, you're coming up with a single number, which is either describing the common value that exists during the entire period of time if the incidence rate function is flat. Otherwise, you're getting an average of maybe similar values, maybe not similar values, depending on what the true shape is of the incidence rate function. And that's why you have to think of the appropriateness of averaging when you're averaging different values together. And that's something to keep in the back of your mind. Okay, that's all I wanted to say about incidence rate. Next time we meet, we'll talk about the relationship between these two measures, cumulative incidence and incidence rate. So I'll see you next time.